Hi everyone, today we are going to talk about the period and frequency and speed of a wave. First we are going to define the wave frequency. So a wave, every wave needs a source. You can start a wave by a source, and every source which produces a wave is vibrating, must vibrate. So it can be a vocal cord while you are talking, or it can be a guitar string while you are playing, or it can be a drum head. So all these are sources which can produce the waves, and the source vibrates, and vibration of the source is transferred to the particles of the medium and produces the wave. For that reason, every wave carries the property of its own source. How many times is the source is vibrating? So frequency, every particle of the medium also vibrate with the same frequency. For that reason, frequency of the wave always equal to frequency of the source. How many times the source is vibrating? Wave also, every particle in the medium also produces with the same number. That's why we say that frequency of a wave is determined by the frequency of the source. Only if you change the frequency of the source, you can change the frequency of the wave. Whatever the frequency of the source is, wave will have the same frequency. Wave frequency describes the number of crests or trough that passes a given point in a unit time. So also it's described as the number of waves that passes a given point in a unit time, because we know that if two crests passes, separation between two crests is called one wavelength. For that, so when one crest passes just after another one, so which means one wave passes. So these two definitions are defining the same thing. So we are going to count how many crests are passing in a given point in a unit time, or how many waves are passing in any given point in a unit time. So both are representing the number of frequencies. So you are going to count right now. So start. One crest passes. Second crest passes at the same time, second wave passes. Third crest passes, third wave passes. Fourth crest passes, fourth wave passes, and so on. You can count them, and you can calculate the total time. After that, you are going to divide number of crests that passes that given point divided by total time for these waves to pass from that point. You can calculate the frequency of the wave. So, for example, assume that there are 12 crest passes at a given point every 6 seconds. What is frequency of the wave? So, according to the equation, frequency of the wave is calculated by number of crests passing this point, total time for those crests to pass from that point. So, 12 crests passes this point in 6 seconds, which is 12 over 6, which becomes 2 hertz is the frequency of this wave. Period is the time. The period is the time required for one complete vibration of the particles of the medium. So remember, wave motion particles are vibrating. Assume that this is the equilibrium position. One particle must vibrate between positive A and negative A. So from negative A to positive A, back again to negative A, this is called one cycle. We are going to count how long does it take to complete this one cycle. It is called frequency period of the wave. Period of the wave is also defined as the time it takes for one complete wavelength to pass a given point. As this particle is vibrating, by the time the wave is traveling, so wave travels a distance which is equal to one wavelength in a time which is equal to one cycle. So when one particle completes one cycle, wave travels a distance which is equal to one wavelength. For that reason, so we can say that period of the wave is also defined as the time it takes for this wave, the wave to pass a given point whose length is one wavelength. And the period is calculated by total time divided by number of crests, or total time divided by number of troughs, which is opposite of the inverse of frequency. And remember, in the simple harmonic motion, we learned that if you multiply period and frequency of a wave, so always you are going to get 1. So you can rewrite this equation to alternative form, just as this in simple harmonic motion. T is equal to 1 over f, or f is equal to 1 over t. A question: if you shook the end of the rope up and down 3 times each second means in 1 second time, total time is 1 second. How many times up and down? 3 times. Up, down, it makes a circle. Up, down, it makes a cycle. So 1 up and down makes a 1 cycle. So 3 times you are doing that, there are 3 cycles. 3 cycles. Number of cycles. So what would be the period of the wave in the rope, and what would be the frequency? We know period is equal to total time, just like in simple harmonic motion, total time divided by number of cycles. Total time is given as 1 second. How many cycles are there in 1 second? 3 times means 3 cycles. 1 over 3 seconds is the period of this vibration. Frequency is going to be 1 over t, 1 over 3, flipped is 1 over 3, 1 times 3 over 1, which is equal to 3 hertz. If the period is 1 over 3, so frequency is going to be 3 hertz. And speed of the wave. Speed of a mechanical wave is constant at a given medium at the same conditions. So one factor which can change the speed of a wave is the medium, type of the medium. For example, sound is a wave. Sound travels in air. Air is the medium in here. So air travels in air at a speed which is 343 meters per second at 20 degrees Celsius. But the same sound travels in seawater, which is the medium in here. Now we change the medium from air to the water at a speed of 1,531 meters per second at 20 degrees Celsius. So as you see, speeds are different because what? The mediums are different. Sound travels in air slower than in water. So only type of the medium, yes, as you see, or some properties of the medium such as temperature determines the speed of a mechanical wave. So if you want to change the speed of a mechanical wave, and the speed of a mechanical wave only changes when wave moves from one medium to another, like from air to water, or from water to air. One of the factors is you should, the wave must change the medium from one medium to another. Another factor is you should change some certain properties of the medium, such as temperature, hot air, cold air, for example, or salty water, pure water, or something like this. So, or soft spring, tough spring. So waves can travel at different speeds through those mediums if the properties of the mediums are different. Same type of the medium, but the properties are different. So waves can travel at those mediums at different speeds. The speed of a wave may be calculated by definition of the speed in kinematics, because speed of the wave in a certain medium is constant. It doesn't change. That's why we are going to use speed equation for constant steady motion. So delta x over delta t. In fact, this is the common equation for calculating speed of an object or speed of a moving thing in a at its constant speed in a medium. Delta x over delta t. We know that a wave displaces one wavelength distance, this is delta x, in a time which is equal to one period, this is delta t. Delta x is one wavelength in a time which is equal to one period. So instead of delta x, I am going to write in here delta. Instead of delta t, I will insert period, which is t. Then I can write equation for speed of a wave, lambda over t. So I can easily calculate the speed of a wave by dividing wavelength by period. And we know that 1 over t, which is in here in fact, normally 1, this 1 over t is also known frequency. So you can write instead of 1 over t f, so equation turns to v is equal to lambda times f. This is more frequently used equation in this book in the calculation of wave speed. Wavelength multiplied by frequency is equal to speed of that wave. A question. A string vibrates with a frequency of 264 Hz. This is frequency. Assuming speed of the sound in air, this is the speed v, is 343 meters per second. Find the wavelength of the sound waves produced in the string. So we know that V is equal to lambda times F. V is given 343 meters per second. Lambda is the question. Frequency is 264. So divide by 264. Divide by 264. Lambda is going to be 1.3 meters. And one more question, this question is towards asking Mr. Exam question, a bit different than the previous one. And a harmonic wave is traveling along a rope. The oscillator that generates the wave completes 40 vibrations in 30 seconds. So oscillator is the source in here, referring the source. It completes 40 vibrations in 30 seconds. So from these definitions, you can calculate frequency if you want. You can need to calculate the period if needed. And a given crest of the wave travels 425 centimeters along the rope in a period of 10 seconds. Be careful about this. This is normally not defining the period of the wave. It's defining time interval. In a period of time, in English, represents delta t, which is 10 seconds, not period of the wave. And in this time interval, 10 seconds, this wave travels 425 centimeters, which is delta x. Delta x is equal to 4.25 meters, which is 425 centimeters. So what is wavelength of the wave? But first we should get speed of the wave in classical wave, which is delta x over delta t, because we know what delta x is, we know what delta t is. 4.25 meter is the delta x. Time for this distance to be traveled is 10 seconds. So speed of this mechanical wave calculated in classical wave, 425 meters per second. Now I will calculate lambda, but I can use calculate lambda only by using the equation of speed of wave. V is equal to lambda times F. V is calculated already, so we can insert in here. We need to calculate lambda, but frequency also needed to calculate. I told you that this is given to you to calculate the frequency. We know that frequency is number of vibrations divided by total time. This is the definition of frequency. Number of vibrations, there are 40 vibrations in total time 30 seconds. It is 1.33 hertz. Now we also calculated the frequency. Then insert the frequency in here. V is equal to 0.425, lambda is the question, multiplied by frequency 1.33. So divide by 1.33, divide by 1.33. So lambda is equal to 0.32 meters, or lambda is equal to, if you convert it to centimeters, 32 centimeters, because sometimes in the wavelength can be given in the choice as centimeter. And according to this equation, V is equal to F times lambda, V changes, speed of a wave changes only with medium. So in the same medium, if you don't change the property of the medium, speed of a wave is always constant. Frequency of a wave only changes with source. So how many times source is vibrating? Every particle of the wave is also vibrating with the same frequency. V and F independent from each other. They are not related. And F cannot affect the V, V cannot affect F. But both F and V can affect lambda. Lambda depends on the frequency, but inversely proportional. Lambda also depends on the speed of the wave, directly proportional. When the speed of the wave is constant, as mechanical waves frequency increases, if lambda frequency increases, lambda must decrease because they are inversely proportional. The wavelength must decrease by the same factor. Assume that according to this equation, in a medium, specific medium, V is constant. You cannot change V. It is constant number. This is constant. If frequency doubles, wavelength must decrease by a factor of 2, so they must simplify. Or if frequency trebles, wavelength must decrease by a factor of 3, so they should simplify. If frequency is halved, wavelength must double, so these two must simplify. So this is always like this. Frequency and wave is inversely proportional in a medium, in a specific medium, while a wave is traveling. But the speed of a wave is independent from the wavelength. Speed of a wave is independent from frequency, because speed of a wave only depends on the type of the medium and properties of the medium. And wave transfers energy from one point to another. Best example is earthquake. Even if earthquake crack is maybe 50, 100 or 100 kilometers away, you can feel it, because this wave traveling through the earth crust carries energy from the source to environment around. So that's why wave transfers energy. But wave transfers energy by transferring the vibrations rather than transferring the material, because transferring material is friction, is effective, very effective. That's why energy is quickly be lost. But in transferring the vibration from particle to particle, energy is not so quickly lost. That's why waves travel longer distance than the material. So earthquake is a best example. An earthquake can affect very, very far distances because energy is transferred through the earth crust by waves. So for above reason, the waves can transport energy more efficiently than other things, other methods. The rate at which a wave transfers energy is called power. In fact, the rate at which energy is transferred in general is called power, and it's represented by delta E over delta T. The rate at which energy is transferred is called power. We are talking about the wave, of course, wave power. It's talking about so the rate at which a wave transfers energy is called wave power. This wave power depends on amplitude of the wave. Even for mechanical waves, the transferred energy is proportional to square of the amplitude. Yani E is proportional to square of the amplitude. Which means if amplitude is doubled, so if E becomes 2E, you should square both 2 and E, it becomes 4A squared. If right side increased by a factor of 4, left side of the proportionality also must increase by a factor of 4, which means energy of the wave increases by a factor of 4. Okay, if amplitude is halved, and if A changes to A over 2, so instead of A, you are going to write A to A over 2. You should square both A and both 2. A square of A is A squared, square of 2 is 4, A squared over 4. If you divide one side by 4, you should also divide other side as 4. So E over 4 is the energy now, as we explained this by energy decreases by a factor of 4, or energy changes by a factor of 1 over 4. Maybe we can say that energy is transferred from one place to another more efficiently than other methods by using waves. But still, energy is lost. It takes longer time, but it's lost. Decrease in the energy of a wave is called damping. As time passes, energy of a wave decreases. That's why amplitude, because energy is proportional to square of amplitude. As energy of the wave decreases because of the friction, amplitude of the wave also decreases. So this is known as damping. Okay, this is all about the section 3. So in next lesson, we will continue with section 4. See you next lesson.